In this lesson, I'm going to be talking about relativistic momentum. So classically, from classical physics, we know that momentum is the mass of an object multiplied by its velocity. And it's given by a very simple formula, P equals mv, where P is the momentum. Okay, it's actually Latin for the word to go and seek, basically. So this is momentum. M is for mass. Mass is measured in kilograms. They're the SI units for mass. And V is the velocity of the object in meters per second. So therefore momentum has units kilogram, meters per second. Okay, and they use P for momentum because P stands for pater. I think that's how you pronounce it in Latin. Consider the case in which momentum is measured by two observers. Suppose you have got two observers. There's observer A and observer B in two carriages. Okay, they're moving relative to one another in opposite directions, so one's moving to the right, one's moving to the left. At the same speed v, and they've got some mass. Each of them have the same mass m, that weighs a kilo, and it's got a spring between them. So there's a spring between these two masses. And now, as they pass each other, this spring is attached to the masses for a moment and is then disconnected. Okay, so suppose as they're passing by, there's no spring when they pass by. When the two carriages are in sync, when they're in the same sort of opposite, when they're in the right position at the right time, whereby the doors of the back and front of the carriage are in the same. Are in line, basically, the weightless spring becomes attached momentarily before it gets disconnected. And so we know that an equal force is applied to each mass by the spring, okay, for the same amount of time. And so hence each mass gains the same momentum. Okay. Now after the spring is removed, when it gets disconnected, the observer in each carriage, the observer A and observer B, measures the velocity of their masses, their 1 kilogram masses, and they can then both agree that their mass moves about 1 meter, so it moves 1 meter across the carriage in 1 second. So 1 kilo mass in each case moves 1 meter across the carriage in 1 second. And so both observers would therefore find that the momentum of each of their mass is given by 1 kilogram meter per second. That comes from the mass of the object 1 times the velocity 1 meter per second. However, when observer A looks at B, so when observer A looks at B making the measurement, they notice that because of time dilation, B's clock is actually running slower. Okay, and hence when B is measuring 1 second, more than 1 second passes for observer A, right? So observer A then concludes that time dilation is due to the relative motion of the carriages, which causes the velocity measured by B not to be 1 meter per second, but smaller. Let me write this down mathematically. So 1 is this, 1 times this. So the velocity measured by B, the observer B, isn't 1 meters per second, but it's smaller. Okay, that's the velocity of B. So it's smaller than 1 meters per second due to time dilation, right? Because of the motion between the carriages. And both observers agree that momentum should always be conserved. Okay, and they conclude that the momentum must be affected by the relative motion. Okay, and if the motion caused the mass to increase by the same factor as the velocity decreased, then both observers would agree that momentum was conserved, right? So if the mass increases, then the velocity would therefore have to decrease to ensure that momentum is conserved. Okay, if one goes up, the other one has to go down. And the observers then conclude that the relative motion must increase the mass by this amount. You can think of this as like mass dilation formula, this statement here. So M sub V is the mass of the object moving. Okay, so this is the moving mass. M sub naught is the rest mass. Okay, object at rest, I should say. Mass of object at rest. So observer A, in other words, is a mass, and observer B, suppose, is moving, and therefore both will measure different masses. So in this case, mass means that, so a change in mass would imply that momentum is relative. It's a relative quantity rather than an absolute quantity. Okay, this is according to Einstein. So momentum is also relative, okay, because mass is relative. Okay, momentum and mass are related by this expression. So momentum in the moving frame of reference will be related to the momentum m, momentum in the rest frame given by this. We can therefore conclude, so momentum in the moving frame of reference given by P sub v is equal to m sub v v. That's equal to m sub naught v over square root of 1 minus v squared over c squared. And you'll notice in these relativistic equations, there's always this factor, square root of 1 over 1 minus v squared over c squared. This square root of 1 over 1 minus v squared over c squared, square root, it's also known as the gamma factor, because gamma is a Greek symbol. It's also known as the Lorentz factor, named after Hendrik Lorentz, German physicist. M sub naught is the mass in the rest frame, the object that's not moving, that's stationary. And M sub v is the mass of the object that's moving. Okay, this is the relativistic momentum formula. So here we can see that momentum is a relativistic quantity. It's a relative quantity and not an absolute unchanging quantity. Now, just to note, as any object approaches the speed of light, so as v approaches c, the relativistic momentum approaches infinity, because the effective mass m approaches infinity. As you approach, in other words, the speed of light, you need more velocity and also more mass, because that's to ensure that P equals mv, this relativistic expression is held, is maintained. So momentum approaches infinity because your mass approaches infinity. Okay, the faster you move, the heavier you get. In other words, faster you move, the heavier you get, according to this expression here. And the heavier you get, the more velocity you need. Right, so therefore the mass and velocity have to go up. If, however, so I'll show you how this works. So back to this expression here. If v approaches c, then the denominator here approaches 0. Okay, because you have 1 minus c squared. Suppose v is c, so 1 minus c squared over c squared is 1 minus 1, which is 0. Square root is 0, 0. Something divided by 0, that results in infinity. So the momentum approaches infinity. And if you recall, the change in momentum is equal to the force times time, right, from year 11 physics. You would therefore need an infinite amount of force to accelerate an object to the speed of light, okay, because momentum is related to force, which is impossible for any material object. So no object in the universe with mass can travel at the speed of light unless you're a light particle. Light particles have no mass. Okay, photons, in other words. Photons don't have any mass. So let's do an example to see how this works. Now, the relativistic momentum equation can be confirmed in a particle accelerator. Particle accelerators are massive machines which smash together particles to study the building blocks of the universe. Okay, it's a branch called particle physics, and it's tested all the time in particle accelerators like the Large Hadron Collider, the biggest scientific experiment at CERN in Geneva, Switzerland, where here you've got protons accelerating up to 0.999999% the speed of light. Right, so almost the speed of light, which is basically 3 meters per second. Okay, that's less than the speed of light. And the relativistic momentum of the protons traveling at this speed is around 8,000 times greater than the momentum predicted by Newton. Okay, a massive factor, massive difference. So the momentum is 8,000 times, roughly 8,000 times greater. Okay, if you use Newton's P equals mv, you won't get an accurate result. Okay, the relativistic momentum formula applies to objects moving close to the speed of light, which is the protons in this case. So suppose you've got protons accelerating to a velocity of 80% the speed of light, so 0.8 c, and we need to work out the relativistic momentum. Quite simply, use the relativistic momentum formula. Now, m sub naught is the rest mass of the proton, which is given by this. 1.67 times 10 to the minus 27 kilograms is the mass of a proton. It's on your data sheet, the HSC data sheet. Velocity, 0.8%, 80% the speed of light, so it's 0.8 times 3 times 10 to the 8, so multiplied by the speed of light. Divide that by the square root of 1 minus, so 0.98 squared, okay? Because v over c, the ratio is just 0.8 in this case. Apologies. And plugging that into your calculator, you get 6.68 times 10 to the minus 19 kilograms meters per second. So it's quite small because protons are quite small. So that's just a sanity check there. Makes perfect sense. And that's how you use the relativistic momentum formula.